Welcome, everyone. Today, we're not just studying physics. We are treating your Cambridge physics exam like a high-stakes legal brief. Think about it. You wouldn't walk into a courtroom without a rock-solid strategy, right? And you certainly shouldn't walk into your physics exams without one. Whether you're taking syllabus 625, 651, 652, 5054, or 9702, the game is exactly the same. To secure those top marks, you need to build your case like a top-tier barrister. You need irrefutable evidence, airtight arguments, and an undeniable conclusion. Right now, on your screen, you're seeing a dynamic split screen showing a real Cambridge physics past paper question, and there's a timer ticking down. Feel that tension? I want you to imagine two students facing this exact paper right now. Let's call them Alex and Sam. Alex is brilliant. I mean, a walking encyclopedia of physics facts. But Alex overloads every single answer with raw, unfiltered data and absolutely zero analysis. Then there's Sam. Sam panics the second that timer starts. Sam rushes, completely missing the specific requirements hidden in the examiner's command words. Look closely at their answers on the screen right now. They are absolutely covered in red pen marks from the examiner. But here's the secret. They didn't lose marks because they don't know physics. They lost marks because they don't know how to play the exam game. In this explainer, we are going to fix that completely. We're going to transform those red marks into green checks. So let's dive into this.
Here is our blueprint for today's masterclass. We'll start by looking at the literal cost of tiny mistakes in measurement. Then we'll move into mastering length and time, unpack the displacement method, and review the golden rules of density. After that, we're shifting into pure exam execution, decoding those tricky command words, and finally, cracking real exam questions together in an interactive workshop. Let's get moving. Section 1, the cost of tiny mistakes. Let's talk about why measurement precision is literally the foundation of everything we do. So why do examiners spend so much time obsessing over measurement precision in physics? Why is it always the first topic in your syllabus? Because it is the absolute foundation of everything in physics and engineering. When Alex just casually writes down a number without considering the precision of the instrument, or when Sam rushes and reads a scale from completely the wrong angle, they are committing fundamental errors. And in the real world, those errors have massive consequences. Check out the incredible contrast on this slide between ancient success and modern failure. On the left, we've got the ancient Egyptian pyramids, built way back around 3000 BCE. A lot of people tend to dismiss our ancestors, but the Egyptians were unbelievably strategic. They used a simple, standardized tool called a cubit rod. Now, originally, a cubit was just the distance from a person's elbow to the tip of their middle finger. But obviously, they quickly realized this varied wildly from person to person. You can't build a massive pyramid if everyone's ruler is a different length. So they established a royal cubit, literally carved out of solid granite. Because they had that uniform, rigid strategy, they built perfectly aligned pyramids that are still standing thousands of years later. Now look at the right side, the Hubble Space Telescope. It possessed the most precisely shaped mirror ever made by modern science at the time. Yet, the original images it sent back to Earth were incredibly blurry. Why? Because of tiny, microscopic mistakes in measuring during calibration. It had the wrong shape by a fraction of a hair's breadth, and it literally cost billions of dollars and a highly dangerous space shuttle mission just to fix it. Alex is kind of like the Hubble engineers here. Lots of highly precise knowledge, but a fundamentally flawed overall execution that ruins the final picture. We want to be like the Egyptians, equipped with an absolute, unshakable standard for our exam strategy. To build that Egyptian-level structure in our exam answers, we really need to start speaking the examiner's language. Look at these three definitions extracted straight from the source text. First up, a standard. In physics, this is an absolute or primary reference. In our exam strategy, the Cambridge syllabus itself is our absolute standard. Second, precise. This means that when you take several readings, they are grouped very closely together. Now, when you are writing an exam answer, precision means your points are tightly focused exactly on what the question is asking, rather than wandering off into irrelevant physics trivia like Alex always tends to do. Third, calibrated. An instrument is calibrated if it agrees closely with a known standard. Calibration in our context means making sure your brain is perfectly aligned with the Cambridge mark scheme. If you truly understand these three words, you understand exactly what the examiner is desperately looking for when evaluating your experimental design questions. Moving right along to Section 2, Mastering Length and Time. How do we ensure our measurements are actually reliable when we're in the lab? Look really closely at the image on your screen. We have a piece of wire laid out against a standard millimeter ruler. Honestly, it seems like the most straightforward task in the world, right? Just measure it. But look at the text prompting us. Where does the wire begin and end? Notice how the wire is actually bent. It's not laid completely flat against the scale. The ends aren't cut perfectly neat. They might be slightly ragged. The markings on the ruler are 1 millimeter apart, sure, but the ink lines themselves actually have width. If you just glance at this, guess a number, and write it down, exactly like Sam would do under time pressure, you completely lose the mark. An examiner wants to see that you recognize these practical, real-world difficulties. Are you actively checking for a zero error on the ruler? Are you ensuring your eye is positioned directly over the mark to avoid a parallax error? This is exactly where your exam answer needs to show critical evaluation, not just a blind, unthinking numerical reading. Before we continue, subscribe to our YouTube channel Ace the Exams at acetheexams_IGCSE to excel in your Cambridge examinations. Click that subscribe button and hit the bell icon right now.
Now, this next slide brilliantly illustrates our point about choosing the right tool. We've got a side-by-side comparison here. On one side, a giant analog clock at a train station. On the other, a highly precise digital clock from a major athletics event, specifically showing Usain Bolt's insane 9.58-second world record, sprint. An analog clock has moving hands, and is typically only used to measure intervals to the nearest full second. It's perfectly fine for timing a slow chemical reaction that takes a couple of hours, or maybe timing a marathon. But look at that digital stopwatch. It provides a direct reading in numerals to a precision of at least 1/100th of a second. Here's the exam trap. If you are asked to design an experiment measuring a very short interval, like a single pendulum swing or a toy car rolling down a ramp, and you suggest using an analog clock, the examiner will instantly penalize you. You must select the instrument that is calibrated to the appropriate precision for the specific task at hand. It's all about context.
All right, now let's step into 3 dimensions. Section 3, the displacement method for measuring irregular volume. Measuring the volume of a regular, perfect cube is easy, right? Just length times width times height. Simple math. But in actual physics, we rarely deal with perfectly regular objects. What happens when you need to find the volume of an irregularly shaped rock or a complex, jagged piece of metal? You obviously can't use a ruler. This is exactly where Cambridge loves to test your procedural, step-by-step knowledge. Let's methodically step through the displacement technique, exactly how an examiner wants to read it. Step 1, select a measuring cylinder that is about 3 or 4 times larger than the object. Step 2, partially fill it with water, just enough so it will cover the object completely, and read the initial volume. Now, crucially, as the source text highlights, you must read the bottom of the curved surface of the water. That curve is known as the meniscus, and your eye must be exactly horizontal to the scale to avoid that parallax error we talked about earlier. Step 3, immerse the object completely. The water pushed out of the way displaces upwards. The increase in volume exactly equals the volume of the object you dropped in. Imagine our student Alex writing a massive, rambling, half-page paragraph about the molecular structure of water right here. The examiner doesn't care. Now imagine Sam panicking and writing, "Put rock in water, see how much it goes up." Sam gets absolute 0 marks for lacking basic scientific vocabulary. You need to use the exact terms: measuring cylinder, immerse, meniscus, and horizontal line of sight. This precision of language is exactly how you secure those top marks.
Section 4, Density Rules. Let's look at how floating and sinking actually work based on the measurements we just took.
So the crucial point here is that once you have the mass from a laboratory balance and the volume from our displacement method, you unlock one of the most frequently tested properties in the entire Cambridge physics syllabus: density. Density is simply the ratio of mass to volume. Basically, it's a measure of how tightly packed the matter is within an object. But Cambridge doesn't just want you to mindlessly memorize the formula. They want you to apply it to predict real-world behaviors. I want you to burn this specific number into your memory right now: 1,000 kilograms per cubic meter, or 1.0 grams per cubic centimeter. This is the density of pure water. It is the golden anchor point for literally all floating and sinking questions you will ever face. The rule is absolute. Anything less dense than water will float, and anything denser than water will sink, period. Ice floats because its density is slightly less than water. A massive steel cargo ship floats not because the steel itself is less dense, but because the average density of the entire hollow ship, mostly filled with air, is less than water. Stop scrolling. Subscribe to our YouTube channel Ace the Exams at acetheexams_IGCSE to excel in your Cambridge examinations. We've helped thousands of students improve by 2 to 3 grade boundaries. Join them right now by subscribing to @acetheexams_IGCSE and turn on all notifications so you never miss our weekly exam strategy sessions. To really visualize this density rule in action, look at this incredible liquid density tower from the source material. We have several different colored liquids: turpentine, olive oil, glycerin, ethanol, and they've all been poured into the exact same glass cylinder. Because they are immiscible, which is a fancy word meaning they do not mix together, they arrange themselves according to the strict, undeniable laws of density. The liquid with the lowest density floats at the absolute top of the stack. The one with the highest density sinks all the way to the very bottom. The exam might literally give you a data table of random liquids and their densities and ask you to draw exactly how they would layer themselves in a beaker. If you understand the golden rule we just discussed, this becomes free marks. The heaviest, most tightly packed molecules sink, the lightest float. It's really that simple when you break it down. Now for a massive gear shift. Section 5, Decoding Exam Command Words. It's time to decode the exact language the examiner is using against you. Listen carefully, because this is where the magic really happens. Every single question on a Cambridge paper begins with a highly specific command word. These words are not chosen randomly by the examiner. They are strict legal instructions telling you exactly what format your answer must take. If you misread the command word, you lose the mark. Even if your physics knowledge is completely flawless, you get 0. This is exactly where our student Sam fails. Let's decode the 3 most common command words directly from the source text. First, calculate. This simply means work out the numerical answer from the given facts, figures, or information. You must show your formula, show your working out step by step, and state the final unit. No unit, no mark. Second, suggest. This means apply your knowledge and understanding to a brand new situation where there might actually be multiple valid responses. You are proposing a logical, scientific idea based on core physics principles. Finally, explain. This is the big one. The syllabus explicitly states that explain means to set out purposes or reasons, make relationships evident, and provide relevant evidence. This is exactly where top students use the PEEL framework, P-E-E-L. Point, evidence, explanation, link. Your point is the core fact. Your evidence is the specific data pulled directly from the question. Your explanation is stating the actual physics law, and your link ties it all back to the specific scenario. If a question asks you to explain, and you just state a fact like Alex does, your grade will absolutely cap out at 1 mark. You have to build the argument. All right, let's put it all together. Section 6, Cracking Exam-Style Questions. Let's put these frameworks to the test with an interactive workshop.
Here is Challenge 1, the data scan. On your screen right now is a table showing the densities of 3 metals in grams per cubic centimeter. We have gold at 19.30, silver at 10.49, and lead at 11.34. Imagine a 60-second timer ticking down in the exam hall. You must extract the core trend immediately. What do we see? Gold is nearly twice as dense as silver. Lead sits right in the middle of the pack. Now here is the setup for our question. Imagine we have 3 solid metal cubes, one made of each of these 3 metals. And here is the absolutely crucial piece of evidence. All 3 cubes have the exact same mass. Keep that locked in your head. Equal mass, completely different densities. Let's move to the actual question and see exactly how the examiner builds a trap for the unprepared student.
Challenge 2, find the flaw. The exam question is, which cube will cause the biggest rise in water level when lowered into a beaker? Let's look at how our 2 students might answer this. Sam is rushing against the clock, sees that gold has the biggest number in the data table, and immediately writes gold, 0 marks. Alex writes a massive paragraph about how gold is a heavy, precious metal and sinks fast, pushing water violently out of the way. 0 marks for Alex, too. Here is the top-tier strategist's logic using the PEEL framework. We know the formula. Density equals mass over volume. Therefore, rearranged, volume equals mass divided by density. Since the mass is identical for all 3 cubes, the metal with the lowest density must physically have the largest volume. Looking back at our table, silver has the lowest density at 1049. Therefore, the silver cube is physically the largest object. Based on the displacement method we learned, the object with the largest volume displaces the most water. The correct answer is silver. You literally have to synthesize 2 entirely different concepts, density and displacement, to crack this trap. Let's move to Challenge 3, speed writing. Look at this final visual puzzle on the screen. A student needs to measure the circumference of a circular copper pipe. Obviously, you cannot bend a stiff plastic ruler around a curved pipe, so what do? As shown in the photograph, they take a length of string, wrap it tightly 4 times around the pipe, and then mark it with green ink. If the exam command word asks you to suggest why the student wrapped it 4 times instead of just wrapping it once, how do you construct that PEEL paragraph before the 30-second timer runs out? Remember, the command word suggest means applying your knowledge to a new situation. Why multiple wraps? Think back to that bent wire we looked at earlier and the massive difficulty of reading tiny scales accurately. Here is the examiner's intended strategy revealed. By wrapping the string multiple times, in this specific case 4 turns, the student measures a much larger total length when they finally unwrap the string and lay it flat against a straight ruler. The brilliant strategy here is to measure the total length, let's say it comes out to 354 millimeters, and then divide that total by 4 to find the highly accurate average circumference of a single turn. Why does this earn the full marks? because any small human inaccuracy in reading the ruler or any tiny gap in the string as it wraps is automatically divided by 4. It significantly reduces the overall percentage error. This is a massive recurring theme in Cambridge physics. Need to measure the thickness of one sheet of paper? Measure a stack of 500 and divide by 500. Measuring a fast pendulum swing? Time 20 full oscillations and divide the total time by 20. It's called the multiple measurement strategy, and it is your ticket to ultimate precision.
We are now entering our final system recap. Look at this quote, taken directly from the Cambridge textbook. It is always important to think critically about the measurements you make, however straightforward they may seem. This is the absolute core of your physics exam strategy. You cannot afford to just operate on autopilot like Alex and Sam. We have covered the 3 rules that guarantee top marks. Rule 1, command word decoding. You must explicitly know the difference between calculate, suggest, and explain. Rule 2, the Peel framework application. You structure your explain answers with clear points backed by relevant data as evidence. Rule 3, the time management matrix. Don't rush like Sam. Allocate your minutes strictly based on the mark value of the question, leaving time to critically evaluate if your method and precision are actually appropriate for the task. Students who implement these physics strategies see an average improvement of 2 grade boundaries, but only if they practice consistently with our weekly videos.
I want to leave you with one final provocative thought to test your brand new strategic mindset. Earlier, we spent time proving that a digital stopwatch is far more precise than a standard analog clock. But as we've learned, precision isn't everything. Think critically for a second. In what specific physics experiment might a simple analog clock actually be the better tool to use? Consider experiments that last for days, or extreme environments where sensitive digital electronics might completely fail. Think about it. Here's your final reminder. Subscribe to our YouTube channel Ace the Exams at acetheexams_IGCSE to excel in your Cambridge examinations. Subscribe right now to @acetheexams_IGCSE and click that bell. Don't let another exam pass you by. Drop a comment below with your target grade for physics and the biggest challenge you're facing. Our team responds to every comment. Like and share this video with a study partner. Ace the Exams, your Cambridge success starts here.